Okay, now let's look at this example. Uh, this involves a spring, which is more interesting than the previous examples. So now let's read the question. The 60 kg rod OA is released from rest when theta equals to 0, right? Determine its angular velocity when theta equals to 45 degrees. The spring remains vertical during the motion and it is unstretched when theta equals to 0 degrees. So first we need to draw the free body diagram and the position of both initial and final of the rod. So this should be the initial position, the black color. So you see here I wrote number 1 here. It means that this is the initial position of the rod. And after it is released from rest due to the weight of the rod has traveled down. So basically, this is the direction of travel. So it goes into position number 2. So, and it says that initially at theta equals to 0, this is unstretched. The spring is unstretched, right? Which means that this is the original length of the spring, original length. Okay, so we see that there is a change of height as well, okay, because this travels from up going down. Okay, so definitely there is a change of height involved. So therefore we have to calculate the work done by the weight. So now let's look at how we can find delta y. So we will take a small triangle here and bring it to here to determine the value of delta y. Okay, so basically you have delta y here, you have 45 degrees over here and also down there, and this is 90 degrees here. Okay, so from this we can use the sine rule. Using sine rule, we can get the value of delta y to be equal to 1.06 meter. Okay, once we have the value of delta y, you can key in the equation to calculate the work done by the weight. Okay, the weight, which is minus delta y times w, and in this case because the rod is traveling down, so you have delta y as minus, and because of minus and minus it becomes positive. So as I have mentioned in the previous tutorial video, if the rigid body is traveling down, then the work done by the weight will be positive, whereas if the rigid body is traveling up, then the work done by the weight will be negative. So you have a positive work done by the weight here, 624.3 joule. Now, the other work done is now by the spring. There is no other work done by other forces here except for the weight and the spring. So in the earlier tutorial video and also the video lecture, I've explained that the work done by the spring is given by minus 1 over 2 k. K is the spring constant, which is given here, 150 Newton meter. This is the spring constant. All right, and you have two variables here, S2 and S1. So basically S2 and S1 is either the compression or the elongation of the spring. And since it says when theta equals to 0, the spring is unstretched, means that at the initial position, the position number 1, there is no elongation or no compression of the spring because it is unstretched. So the spring initially has its original length. Therefore, we know that S1 equals to 0. Okay, because no elongation. So remember, S1 and S2, these two are the elongation. How long the spring has deformed. It is not the length of the spring, but it is how long the spring has deformed, has elongated, or has compressed. So because in the first position, the spring is not stretched and the spring is at its original length, therefore no elongation involved, so S1 equals to 0. Right. Now S2, you look at the green spring here, this one, this is definitely the spring has deformed, the spring has elongated. So if you can guess where is the elongation of the spring, it is definitely this length here, right? This is S2. Okay, it is not including this because this is the original length. So the elongation S2 is basically only the bottom part of the spring minus the black part. So how do we find this? We can generate a triangle from here. Okay, you see that this, we can get a triangle from that, and to calculate what is S2. Okay, so I have extracted this triangle here. So you know that this is S2. Okay, you have here 3 because initially we have calculated that this part is 1.5, the half of it. So that must be 1.5 multiplied by 2. So you have 3. All right. And we can go ahead and use the sine rule again, using sine rule to get the value of S2. So now you have S2 equals to 2.12 meter. Now once we have all the values, we can substitute in this equation US. So you have minus 1 over 2. The spring constant is given as 150. S2 square is 2.12 square minus 0 because S1 equals to 0. So you will get the spring constant, sorry, the work done by the spring is minus 337.5. So you notice that the negative sign here is for the spring, the stretched spring. Okay, if the spring is compressed, I believe the work done will be positive. Okay, it's either that. Okay, all right. So now again it says that released from rest up here. So we know that the initial kinetic energy, initial KE, is equal to 0 because it starts from rest. The final kinetic energy, this is a pure rotation, rotate about O. This is rotation about O. So you can use 1 over 2 IO omega square, and we need to find what is IO. Okay, IO, you can use parallel axis theorem. Use parallel axis theorem. Before that, to use parallel axis theorem, you need to know what is IG first. So this is a slender rod, 1 over 12 ml square. So you have IG is 45 kg meter square. Then you can use this parallel axis theorem. Okay, parallel axis theorem. Ig you have 45, m is the mass 60 kg, and d is the distance from point G. Okay, this is point G over here to the center of rotation. Okay, to the center of rotation. Also, you have that is definitely half of the length of the rod, which is 3 over 2 is 1.5. So you have IO equals to 180 kg meter square. Then we have T2 is 90 omega 2 square. So then we apply the principle of work and energy. I repeat again, this equation over here is the principle of work and energy. Principle of work and energy. Okay, so T1 equals to 0. Total work done is the work done by the weight plus, or actually minus, the work done by the spring, equals to T2 is 90 omega 2 square. You solve this, you will get omega 2 equals to 1.785 rad per second.